Okay, so I guess we can start. Good evening, good afternoon, everyone. Welcome at C&O department. I guess for many of you, it's probably first day at C&O department. I hope it's one of many to come. So today we have a special seminar, and it's done by Professor Jane Gao. Professor Gao did master's degree and PhD degree here at Waterloo, and then was a Humboldt Fellow, and so Humboldt Fellow at Max Planck Institute in Saarbrücken, and then was NSERC postdoctoral fellow at University of Toronto, was also a professor at Monash University, and recently, or not so recently, I don't know, actually, depends how to count, came back to Waterloo as a professor, faculty member here at C&O. So today we have a pleasure to listen to a talk by her on representable matroids.
Thank you, Kostya, very much for the introduction, and thank you, everyone, to come to my talk. So, as the title says, I'm going to talk about evolution of random representable matroids. And in general, my research combines probability and discrete structures. And most of the time, I work on graphs. Of course, when you combine with probability, it's called random graphs. And sometimes I work with random matrices. And today, I'm going to talk about something that's related to the matrices and graphs, and that's called matroid. So if you haven't, heard about matroid at all, it doesn't matter at all as well. It's because I'm not going to really talk about the general matroid at all. I'm just going to talk about representable matroid, which means you can understand what's going on as long as you understand matrices. All right. So let's talk about what is the motivation of this research. It's motivated by something called the random graph process, which is how random graphs were introduced in 1959, 1960s by Erdos and Renyi, and now it's a very popular and well-known random process. So it starts with n vertices and without any edge, and every step you just join two vertices uniformly random as long as they are not joined by an edge. So step by step, you draw edges. So this is after 4 steps of the process. And this one you can count. I'm not very good at counting, but then at some snapshot, you will see some graphs like this, and then you will see a graph like this. By the end of the day, you will see a complete graph, right? And usually in this field of study, you will not be interested in any graphs with so many vertices. You will typically let the number of vertices goes to infinity, and then study while n, the number of vertices go to infinity, what kind of properties of the graph have or do not have. And then in the first paper where this model was introduced, there was a very striking phenomena. It's a phase transition that was proved by Erdos and Renyi, was that precisely around the time, this is p, or you should think about as n over 2, which is the number of steps. So about, if you wait for n over 2 number of steps, then you will see a big giant component, which means small pieces of components appearing here will start to join together and then form a large component. That happens exactly, very precisely, around the time n over 2. This is the probability of 2 vertices being joined together. So then you keep adding edges, and then you will see different structures that's going to appear. For instance, when the edge density becomes log n over n, that's roughly speaking, the number of edges is going to be n over 2 times log n, okay? And that's the time that you will see a perfect matching, if you know in graph theory what perfect matching is, or a Hamilton cycle, or it's just the graph becomes connected, okay? The vertices that are isolated start to disappear. And around this time, so this is much later, the density of the edges become n to the minus 2 over 3, that's the time a triangle factor starts to appear. Triangle factor is the two regular graph spanning where every component is a triangle. So if you ask when a triangle will appear, it's here. But much later, you will start to see a triangle factor. And then you can also ask when is a clique of size t going to appear. That's something like that. OK, there are endless list of questions you can ask here. But this is not something we are going to discuss today. But it's just a motivation of some kind of evolution of some random processes that we want to study. And why don't we study random matroids of this type? OK, so before we get in there, let's just introduce what is a matroid. And as I mentioned, this slide really doesn't matter so much as a general definition of matroid. So a matroid is a pair where you have a ground set, which is a finite set, and then you have a family of subsets. They're called independent sets. It's not every subset can be a independent set. They have to form some kind of axioms. Simply set, your independent set should contain the empty set, and it should be downward closive. I don't know what's the English word, which means a subset of an independent set must be independent set. And also, if you have two independent sets, one is bigger than the other, it must be that you can take one element from the larger one, put it in the smaller one, and you form another independent set. This is something very familiar if you recall it from linear algebra, right? And that's why it's connected to matrices. So how is it connected to graphs? So there are a type of matroids coming from graphs called graphical matroid. You just take a graph and then consider E to be the set of edges in the graph. And then the independent sets will just be the set of forests in your graph. Then you can easily check that all those hypotheses will be satisfied. OK, how is it related to matrices then? Not always, but there's also a class of matroids called the representable matroid. So it's a type of matroid that you can written in the following way. You can represent every element in E, the ground set, as a column of a matrix, whereas independence is linear independence, basically. So any a set of elements are independent in E, which means an element here, if and only if these corresponding vectors are linearly independent. So in my talk, I typically just draw 0, 1 matrices, but you can think about matrices over any field, all right? And then most of the results I'm going to talk about is over any finite field. Any questions? All right, so I'm going to introduce two probabilistic models for the evolution of random matroid. The first one is just so sweet and nice and clean, and therefore I put vanilla here. Just means it's really, 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 really nice. If you see the proofs, it's really, every proof is very simple, okay? Compared to the second model, I hope I don't have time to talk about. Anyway, so how do you construct this one? You start with empty matrix, and then you just add columns one at a time. You will have n rows. Something you can think about n as like number of vertices in the graph, right? So there are n rows, and every entry is just a uniformly random element in your field. And in this case, I'll just put 0 or 1. OK, that's my first column. That's my A1. And then I add a second column. I call it A2. I add another column. It's A3. Every column is drawn uniformly at random. And then I get, in general, it just keep going. I get AM. And then I study the matroid represented by this random matrix. OK, so that's the first model, the vanilla model. It's proposed by Keeley and Oxley in 1984. And even before that, they already have an analogous model, which I don't even want to introduce today, but they are sort of equivalent. So instead of drawing those independent columns, you are adding elements from projective geometry with either some density or a certain subset of certain cardinality. But up to some point, all these three models are equivalent. All right? So we'll just focus on the first. So we'll study a few of those matroid problems because we don't want to study them as graphs. The first thing it's you probably will think about what are matroid problems. Well, one is the rank. You also study bases. You want to study circuits. I'll introduce all of them, okay? And the connectivity and so on. So all of those definitions are somehow coming or motivated by concepts you see in graph theory. So what is the rank of a matroid? You have independent sets. So you look at a maximum independent sets and look at the cardinality. That's the rank. But we are talking about representable matroid. So you just look at the matrix that's representing it, right? And then look at the rank of the matrix. So it's really nothing to do with matroid anymore. You just look at the random matrix and study the rank of it. And we'll see soon why we call it a vanilla model, because you will see it's so simple. It's easy to prove is that, okay, you have n rows. The rank can be at most n. So let's ask the first question. When is the rank going to be n? Or how is the rank going to evolve in this process? It's easy to prove that slightly before you reach n steps, all the columns you added are linearly independent. And a matroid like that is called free matroid. And it's just a constant steps until you reach n. And then if I'm giving you a few extra columns, you can prove that with high probability it's going to reach full rank. And then the rank doesn't change afterwards. All right? Yes?
Sorry, what's the field that you're considering?
Any finite field. And if you are thinking about field like real, then it is actually exactly here at n. So before n, you get, before or at n, they are all linearly independent. And after n, you will have first circuit. Okay, but with finite field, you do have a constant width. Yes?
The constant in the O depends on the finite field you're looking at?
Sorry?
The constant in the big O term depends on the specific.
Oh, yeah, it's a very good question. So all the big O notation are respect to n. So we will let n goes to infinity.
Okay.
Yeah.
The order of
that's independent of n. So you fix, let's just say 2 for this talk. It's easy, right? It's just binary matroid. Okay, so let's just see how simple the problem is. I'm just going to give a toy example of showing what's the probability that you add n columns and they're all linearly independent. Okay, and then we just do one step at a time. And every step, the column that you put in has to be linearly independent of all the columns you have added so far. So of course, the probability that's independent before, the first one is 1. And the second one, there's only one column before. So the probability that it doesn't fall into the span of the previous one is just q over the total number of vectors is q to the n. And then the second time is q squared over q to the n, and you make a product of it. And it converges to some constant. When q is 2, it's something like 0.3, but it gradually goes to 1 if you make q goes to infinity. And that's maybe give you intuition why in the field of real numbers, it's actually 1. All right. Okay, so this didn't prove this thing, but triggering this argument a little bit, I'm pretty sure with a bit of exercise, you can prove that a little bit before n, this part is going to be free matroid. And if I give you a little bit extra, you will see full rank. All right. Okay, next let's discuss circuit. So what is circuit? It corresponds to cycles in a graph. If you know cycles in a graph, so the purple thing is called a cycle. And in matroid term, it's just a minimal dependent set. Right? So this is the matroid, graphical matroid. So it's just the incidence matrix of this graph that I'm drawing on the left. And then these are the 4 edges in the circle. So you will see if you add them all together, you get a 0 vector. So it's linearly dependent, but any subset is linearly independent. All right, so what about circuit? It's indeed already studied by Kelly and Oxley and Kodecki and Wuchek around 1984 and 1999. It's fully studied. And I just want to point out some interesting corollaries from their findings. All right, so the first circuit, of course, appears at the time that the columns stop being linearly independent, so it's going to appear somewhere around n. And what happens? Okay, good. Where am I? And then somewhere in linear number of steps, you will see circuit of length linear in n. So if you say, okay, one is a Hamilton cycle is going to appear, which is a circuit of the longest possible length, right? It's actually appearing after linear number of steps. However, short circuit is much harder to appear. You have to wait much, much longer. So circuit of length much smaller than n appear around this time. So this is already super polynomial. Oh, maybe the connection. Okay, it's
Okay, maybe
hopefully it's good. It's here. And then maybe think about the smallest possible circuit, which is of length 3 if you restrict to simple matroid, and that's the time, q to the n over 3. Very much, near the end of the process. And if you go even further, what you are going to get is non-simple matroid. So you will see duplicated columns at some point. All right. So what kind of corollary we can see? First, maybe interesting question is you look at the first circuit that's going to appear. How large is it?
Sorry, I feel like something. I'm not sure whether we will be able to. This is really a cursed room, I feel like, for projecting.
A cursed room. Or maybe because the topic is random, so they want to show up in the random time. So this is a plot. We just plot the result. And this is the length of the circuit scaled by n, okay, alpha n. And then here is the time, m. So the first circuit appears here, right, around time n, 1 times n. And the length, you can see here, is 0.5. And this is the plot for q equals 2. And in general, the length is q minus 1 over q. And it's not symmetric, this function, so which is understandable on this side, right? Because we already mentioned that the smaller circuit appears much, much later. So you need to wait very, very long to get small circuit. However, what's interesting here is that the Hamilton circuit always appear early. It's actually, no matter how big Q is, it's always bounded by 2 times n. And then this is the plot for Q equals to 2. So you see that it appears before 1.4 times n. All right, so it seems that we understand everything about circuit. Let's move to the next concept called connectivity. So it's, again, a concept coming from graph theory, right? So this is a separator of a graph. You remove those 3 purple vertices, then you separate the graph into 2 parts or more. And it's a 3 separator because there are 3 vertices that separates them. So how can I define such a thing using matroid terms only? Right, there are no vertices or anything like that. So we can do this. Is there color?
Yeah.
Oh, there is color, right?
It's yellow and blue. And
This is blue.
Yeah.
Oh, you can see. I can't. Anyway, so this is I just partitioned the set of edges into 2 parts. One part is blue, called X. The other part is yellow, called Y. And we notice that the rank is at least 3. Yeah, we want this requirement to make sure when you separate, there's something remaining here. And the other thing we find is that if you add the rank of the blue, add the rank of this yellow, and then subtracting the rank of the whole thing, you get 2, which is 3 minus 1. This 3 relates to this 3 here. So okay, it's not exactly 3, but it's only offset by 1. And it's not a big issue for mathematicians. So we can just take this as definition. If you check through examples, you will see that this can be generalized. So this is what's called vertical K separation. And the smallest k, where there's a k separation, is called the connectivity, okay, of the matroid. So what's the definition? You want to partition your ground set into two parts, x and y. Both of them must have rank at least k, and then you have this, right? Summation of the rank, subtracting the rank of the original one, has to be at most k minus 1. There's another notion called TUT separation, where it just replaces the rank by the size of those two sets. I'm not really matroid people, so I actually don't really know the intuition in the literature why there are different notions. But I guess they mean something. And there are even more notions, but not related to something like a vertex connectivity or edge connectivity. There's also something called cyclic connectivity. But in this talk, we are only going to restrict to these two connectivities and then see what we can prove. All right, so this is, I just want to use a figure to illustrate what's going on with those connectivities when you add columns one by one. So first thing to notice is that the vertical connectivity, even by the definition, it's not clear it's a monotone property. So it is possible that when you add more edges, I shouldn't say edges, add more columns, it's possible that the connectivity actually drops, which is different from graph case. However, in random matroids that we constructed this way, we can prove with high probability it's monotonely increasing, at least non-decreasing. All right. However, the TUT connectivity will match vertical connectivity for a while, and at some critical time, it's going to decrease. And this is the picture for TUT connectivity. And why is it like this? And it's by this proposition, which basically says if your matroid is not some kind of special type, which I don't want to define here, then the TUT connectivity of your matroid, which is the blue one here, is the minimum of the vertical connectivity and the girth of the matroid. We know everything about the girth, right? Because we already studied the circuit. So once we know the vertical connectivity, and we know the girth is dropping.
I can bring that up on new computer, it depends on. With this problem, this room has, some problems.
Maybe people don't mind to take a break from time to time. Yeah. All right. Okay, so girth never increases. And it decreases eventually. And that's why up to some point, the TUT connectivity is completely governed by the girth. And this is just basically this part of the picture is just the girth of the matroid. And that's why you see this picture, all right? So I just want to quickly mention the critical time where the matroid becomes K-connected, and I denote this by tau of K-connected, was fully determined when K is a constant, 1, 2, 3, 4, 5. And also it's upper bounded when K is linear in n, say 0.5 times n or 0.1 times n. What we did is that we determined this hitting time when K is smaller than n. So say log n or square root of n or n to the 3/4, something like that. And then we tried to close this part because they only proved the upper bound. So we proved lower bound, but unfortunately we were not be able to prove a matching bound. So currently there's still space, gap between the upper and lower bounds. And as I mentioned that, this picture, right? This part is completely governed by the girth. But just because for this part we don't have the upper and lower bounds has a gap, and therefore in order to determine when they start to differ, this beta star, we also only get to bounds. So once you can improve the upper bounds and lower bounds over here, then you can also improve or even determine beta star. So this is just a plot of the bounds. So this is the upper bounds obtained by Kelly and Oxley, and this is the lower bounds we obtained. It's roughly like a half of it. but there's no way that I believe it's half of it. And it's a complicated formula, and comes completely from different way of counting, so I couldn't see which one is tight either. And it's possible that none of them are tight. All right, yeah?
Finding this gap between the upper and lower bounds, like, is there value in like doing a whole bunch of random samples and seeing where it actually lies, or does that not give you any information?
It's always high probability. So we just prove that, for instance, you take k is n/2, and then you say how connected it is. We prove that up to this time, with high probability, it's going to be k connected. But if you only wait to this time, then with high probability, it's not half n connected. But I think it's concentrated. But unless we prove it's concentrated, we cannot say anything about it. Yeah, thank you. OK, so just adding the result to that picture, you will see k connectedness. When k is much smaller than n, everything occurs around this field. This is a very crowded landmark, many events occurring over here. However, there's a critical value alpha n over here where the matrix becomes fully connected and connected. OK? And then if you zoom in here, then we can, for every k that's sublinear, we can say precisely around what time that the matroid becomes k connected. All right, now let's talk about coloring. So coloring graphs, I guess everyone knows. You give a color to a vertex where adjacent vertices receive different colors. How can we define coloring in a matroid using only matroid terms? Probably I can color the rows. Right? OK, so let's just take the same color. So here will be white, and this one is yellow, and these two are red. And then what do? I just add these white rows together, and I get a new white row. And I add all the yellow rows. There's only one, so I just copy it down here. And why is it useful? Now I look at these two, or maybe just look at the matrix with this row and this row. What I see is that every column is hit by some non-zero element. So I just say all the columns have been hit or covered. OK, so that seems to be a definition, because it only uses rank or row space or whatever. So this 110, is just a vector in the row space of this matrix, right? And then this one, again, is a row vector in the row space. And then they satisfy a property that if you take these two row vectors together, then they hit every column of the matrix A. Of course, I only use 2 here, and then the coloring number here is 3. But again, it's just offset by 1, and we are not bothered by that. All right, so this is the definition. It's k-colorable if you can find k vectors in the row space of A that covers all the columns of A. And our main result is that we determine precisely when the graph stops being k-colorable. Okay, it's actually a decrease. I mean, the parameter is increasing. So the coloring, or if you call it chromatic number, but actually in matroid it's called critical number. At some point, a critical value that is going to stop being 1 colorable, and then it will stop being 2 colorable, and stop being 3 colorable, and that's the critical time. And then we determined all those critical time until it's going to be very, very close to the end, but by that time you just use some trivial upper bounds, just like if you are going to complete, if you are going to say chromatic number of a complete graph, it's n, right? That kind of trivial bounds already is pretty good when k is very close to the end. Okay, yeah. So in the picture, it just says that we know exactly when the critical number or chromatic number jumps from 1 to 2, from 2 to 3, and 3 to 4. If you care about exactly the time, this is the formula. It looks a little ugly, but it has a little bit better looking. If you let k goes to infinity, then it's a little bit cleaner. So it's some formula like this. Any questions? Sorry, this title is wrong. It should be critical number. Okay, finally, let's come to the minus, because if you're studying matroid, I think it's non-avoidable to talk about minus. So minus of graphs are graphs that's obtained by sequentially performing a set of operations called deletion and contraction. So deletion is just you specify an edge and you delete it from your graph. It's like this. So how do you do that for a matroid? You have one column, and they say you want to delete it, and they just delete it. And it's deleted. Okay. And now, what is contraction? You want to contract this edge. Basically, you can visually think about merging these two vertices together, right? And then, well, you create some multiple edges here. It depends on the definition. In some situations, depending on the problem you want to study. But for us, maybe it's convenient just to keep the multiple edges. Okay, so how do you do that in the matroid? Say I want to contract this element. I just do row operations to make this one a single one, and all the others are 0, right? So I just subtract this first row from the second row, and then this row becomes like this. The other ones, I don't have to do anything because they're already 0. Okay, so just simple row operation. And then once I do that, I delete this column, delete this row, and I get a submatrix, or a matrix like this. Look at the matroid represented by this matrix. That's going to be the minor of the original matroid you start with. Okay, so now we have extended the definition to matroid, and now we can study minus of random matroids. So this has been studied in 2017 by Altshuler and Yang. What they said is that if you fix any minor, right, any minor of fixed size, they all appear around at the same time. Okay, the first, the appearance of the first circuit. So exactly in the same window, all of those minors are going to simultaneously appear. What we are going to prove is just strengthening their results in multiple ways. The first is that we are going to determine very precisely the limiting distribution of precisely the step where a given matroid is going to appear as a minor, not a limit, not something like this. So in the next picture, you will see how different these two results are. So here is 0 is really just corresponding to n, okay? And I'm going to go offset on the left and then right. And this plot is matroid, I think with co-rank equals 1, and q is a half. So it's a binary matroid. Just using this result, I plotted the point-wise the probability mass of this hitting time. So you can precisely say at this point, like say m equals n, the probability that the minor of that particular minor appear precisely at that time is this probability. Okay? And then if you look at the CDF, cumulative distribution, that's the red spot. Okay? So it becomes 1 here already because the probability mass of here are all equal to 0. So it's kind of interesting probability where here you have a sharp tail, whereas over here it really goes to 0 immediately at a specific value, which is very different from here, right? You look at the window of some kind of growing size. And this is the bound by Altshuler-Yang. So what they obtained is an upper bound on the left-hand side, a lower bound on the right-hand side. And you can see that the result doesn't give any information locally around n, so in that window. And it only gives some kind of qualitative property when this goes to infinity on both sides. And that's the difference. All right, so that's part A. And then also we prove a hitting time result. So what's quite interesting is that the time that you see a specific minor, say n minor, it appears exactly the time that your matrix, random matrix, has the co-rank equal to the co-rank of your matroid that you are looking for. Okay? And those are for fixed size matroid, but you can let the co-rank of the matroid grow, but not growing too fast, then we can prove a 1-point concentration. So we know exactly with probability, roughly speaking 1, that the minor is going to be created in that step. Not before, not after. And also, okay, you can ask what's going to happen if I make n really, really big. It's going to violate this. We didn't work out that, but we just look at some specific type of minor, which is the complete projective geometry. When R is much greater than log n, we determined the time that it's created. And when R is smaller, it just follows from somewhere ABC, okay? And what's interesting is when R is some constant times log n, we actually don't know the answer. So this part is still open, and I think it's interesting, and I don't know how hard it is. Our proof couldn't really cover that open range. All right, so let me just quickly tell you how to find minors, because the proof actually is very simple, and I think it's still good to have a proof for each talk. So this is going to be my proof. All right, so suppose n is the minor you want to look for. Without loss of generality, because you can always do row operation, right? I'm just going to write this part as identity matrix. So the rank of the matroid is R, so it's a R by R identity matrix here, and then you have co-rank equals K. So it's just some vectors B1 to Bk. I want to look for this structure by doing contraction and deletion. Let's assume that A looks like this. There's identity matrix, n by n identity matrix here. And you already noticed that I'm cheating, because, of course, it's not necessarily has full rank. But life sometimes is much easier when you're allowed to cheat. So I'm just going to cheat a little bit here. And I just assume here I have A1 to AK, okay, which the number matches the B1 to PK here. Well, something really make the vanilla is that this A1 to AK all have uniform distribution. Because those are already not from the original drawers of columns, right? You have to perform row operation to make this part identity. And the nice thing is after you do that, and then you look at the elements over here, they are still uniform. All right, so what do? I just keep this part R by R, and then contract everything here. So what does that mean? I just delete those columns and delete all those rows. What's remaining is an R by R matrix here and a bunch of columns here. And I just have to show that this part equals this part. What's the probability of that? Well, maybe not very good. And I even don't want to be clever to have really good bounds. So this is just a stupid bound. I say, OK, what's the probability this vector is equal to B1? It's a uniformly random one, so it's Q to the minus R. And then I just multiply K times, right? And why I can do this? Because I can look for it here. I can look for it in the next R rows and next R rows. And I have N over R rows. And then the probability none of them are successful is going to be very small. So eventually it goes to 1. And that's the proof. And of course, when you have to prove hitting time result, you have to be a little bit more clever. But it's really not so much more complicated than this. OK, any questions? Yes?
So this depends on the co-rank.
Mm-hmm.
Can you speak to the intuition behind this?
So co-rank gives an obvious bound, because if your co-rank of the matroid is smaller than the co-rank of the minor, it's not possible. Because when you do contraction and deletion, the co-rank is not going to increase, right? And then that's why it's tight. So the result you really want to prove is that as long as the co-rank matches, then you immediately find your structure. Yeah. But it's not, the proof isn't much, go away from here. It's not very far from here. Okay, there are some other known results that I'm not going to cover in this talk anymore. So for instance, same as studying small subgraphs in random graphs, you can study threshold and limiting distributions of small submatroids. And those has been studied by Oxley and Kodaki in different years. All right. Okay, so too bad, I still have some time. So I have to talk about the second model. All right. Okay, so this is a vanilla model, right? So all the columns are identical, independent. And I mentioned this one. So you just take any invertible matrix P, okay? And then you take a uniformly random vector V, you multiply P on the left, you still get a uniform distribution. And this is very, very nice, sometimes so nice to be true when you deal with random structures. And it's a crucial observation for all the proofs to work. And also, very often when you're dealing with random structures, you have to study conditional probabilities and so on. And in this probability space, even if we restrict to certain subspaces, it's still uniformly distributed. All right. Okay. So what is this one? I put a coffee bean here. Not too offensive for people who like the coffee, but it's just it's bitter, but still it's fragrant. So they are also composed of IID columns, but besides that, everything is non-trivial, and you will see quickly why everything becomes so difficult. Let me define it first. What's the first column? So you still add columns one by one. But now let's fix a constant k. In this case, k equals 3. So I'm going to uniformly pick a vector whose support size equals 3. So exactly 3 entries that's non-zero. In a binary matrix, it just means 1, right? And the next one is the same. And the next one is the same. The next one is the same. And I keep going. If the support size is 2, you will see that it's exactly the incidence matrix of a random graph. And then you can think about here is the incidence matrix of random hypergraph, K-uniform hypergraph. All right. OK, so back to vanilla case. We have seen a proof of the probability of AN. OK, you say exactly n steps. What's the probability as full rank? We proved that one. It's just a one-line proof. And what's the story here? In this second model, it's not going to have full rank. In fact, even if you give any linear number of columns that you added, you will see a linear number of all 0 rows, just by coupon collection. If you think for a moment, you will see it. So the rank is never going to be full. So now the question is really, if you add linear number of rows, what is the rank of your matrix? That's pretty much the first question you can ever think about it when you think about matroid. All right, similar picture is going to happen. You wait until some critical value, and then before that, you get a free matroid, which is understandable, right? When you initially start to add columns, they are going to be linearly independent. And the question is, when they stop being linearly independent, and it's utterly difficult to study this problem already, and with a long history of research, starting from k equals 3 and the binary matrix q equals to 2. And then each step of progress involves non-trivial new ideas of new proofs. And eventually, we proved everything about every k and every q and even other field. But anyway, at least this part has been solved. Okay, so we determine precisely what alpha star, which also is non-trivial, where it is. But by that time, it's free matroid. I think it's every time when I try to click.
Oh, really?
Yeah.
Do you want to unplug?
OK, so now this is the picture after. So after that, of course, it's not going to be, the rank is not going to be, the number of columns, but rather it's going to be some function, right? M is some alpha times n, and then the rank is not going to be alpha times n, but some function alpha, f of alpha times n. And again, it's very non-trivial result. Again, I'm not going to talk about this. Involves really, quite non-trivial treatment. But at least we know the rank. At least asymptotically, we know the rank of this matroid. And the next thing we know is about minors. And the first result is by Cooper, Fries, and Tegden in 2019. I think they announced the result a few years earlier, but it was first appearing in 2019. So they studied in binary matroid. Okay, suppose size of k, but their result requires k to be sufficiently large. And then they fix a binary matroid and study when this binary matroid is going to appear as a minor. And what they say is just that it appears in linear time. M over n, m is the number of columns. You have to add so many columns that m over n is really large. So it is really already way after the critical time that actually it appears as a minor. So the natural question, and it's also just asked by them, is really where is the threshold? Right? They didn't capture the threshold. And also this finite field, the two here, it really plays a crucial role in their paper. And we want to have answered the question about any general finite field. And also k being large is really somehow ridiculous because you feel k shouldn't play a role. It's just the size of support. So we know k equals to 2k's, and then we know the case in their result k really large. But it should be the same for any k. And then here's our result from last year with Peter Nelson. So basically, we answered all these questions. K is just any number, at least 3. Because k equals 2 is the graph case, right? Random graph case, we already know. Q is any finite field of order Q. And N is just any representable matroid. And then what we proved is the time that N appears as a minor is roughly this magical number you have seen before. It's roughly the time where the first circuit appears. Okay. Okay, so I still have a bit of time. So let me just talk a little bit of why it is so difficult here. Hi. So if you recall the proof of the vanilla case, we make use of the basis, right? We start with A that has a basis, and then we try to find the other vectors on the right-hand side. And now where are the bases? We don't know where the bases are because it doesn't even have full rank. So initially, we tried to do some kind of operations like deleting all 0 rows, and then do other operations and then just trying to prove that after those operations we get full row rank, and then proceed from there. And we get a lot of headache. And still, I don't know. It's actually, we always prove something close to be true, but not really true. And then in the end, we gave up. So the idea, oh yeah, sorry. It all came. The idea is not to use the basis to build minor, but I don't want to extend further from there. So we have to have some new ideas. And the other thing is really, you can already imagine, we want to, it's the same as before. We want to build this identity matrix, right? Which means you have to do row operations. And the row operation is just some matrix, invertible matrix you apply to the left-hand side to make this part or 1. So roughly speaking, you want to multiply AM by this invertible matrix P. Okay, after you apply this, then all those VIs left over is just P times VI. And now they are not uniform distribution anymore. I actually don't know what the distribution is because I only know distribution of the VI, but I have no information about distribution of this P. P is just some inverse matrix of this weird square matrix that I don't know the distribution itself. So a major obstacle is the distribution of P. Okay, so how are we going to find the minor? So again, this is the target I want to look for. Suppose I have, after row operation, I get some structure like this. I do exactly the same, right? Keep the R part here, and then get something like this. All right, so basically I want to find a structure, this part, that contains those vectors. Now I allow it to be some linear number of columns, just makes problem a little easier. Otherwise, there's just no hope to succeed. All right, so this is just taking the first R rows of this P matrix, and I have to multiply by this VI, which has, say, exactly 3 ones out of some random place. So what is this multiplication doing? It is just taking 3 random columns of P, add them together, and then see, okay, what's the probability when you add them together, you get one of those BIs. Intuitively, if you can say that, okay, these PRs have all vectors that you want to have here, let's say, or all vectors in FQR, many, many times, so I have a good chance to hit each of them, then probably I can prove something like this, except we cannot prove it, but we can prove something close enough to get what we want to prove, okay? So I don't want to define things. These are very technical, but roughly speaking, P has to be very dense matrix in a very strong sense. And then we have to use multiple rounds of sprinkling of columns in multiple rounds to build the structure we want. And then we actually, I'm cheating a little bit here. I'm not taking R by R to directly looking for N. But if you know matroid theory, you probably recognize this growth rate theorem, which just says that if you find, okay, you are looking for some small minor, let's look for a much bigger minor, much bigger, but it has quadratic number of elements, then this theorem says that it contains your smaller minor. And somehow this is really convenient to be used here to find our minor, to really be able to catch all the way to the threshold. All right, so that's the idea. So let me just finish the talk by quickly mention that there's another random matroid model which might be a little bit more natural, but much harder to study, is the uniform model. Just like random graphs, the most natural model would be graphs with uniform distribution, right? So here you can think about matroids with, say, n elements, but that sample uniformly random. It's very hard because I couldn't think of any probabilistic treatment that can easily apply here except for counting. So I can imagine that all the work that's listed here are counting results, just counting counting matroids that are, say, representable, counting matroids that are connected, and so on, okay? And very often you get some bounds. But if you're lucky enough, those bounds are enough to say something. In general, you can define other random matroid. You just take any matroid that you like, and then take some probability P from 0, 1, and then you keep every element in your matroid with probability P independently. And then you get a submatroid. And that's interesting already, right? So the things that we studied earlier are special models of this. If you take M to be the projective geometry, that's exactly the vanilla model. And if you take this to be all hyperedges of the complete RK uniform hypergraph, and then you get this model. Then, of course, you can study something even more general, crazy. I don't know. Anyway, let's go to the open problems. These 2 open problems I already mentioned in my talk. So these are the problems we didn't manage to solve. One is the complete projective geometry of rank R going to appear in the vanilla model. We don't have an answer when R is of order log n. And also for the time that the matroid becomes k-connected, where k is linear in n, there's upper and lower bounds which don't match right now. I think we can even study other problems. We just didn't have time to get to it. So we can study automorphism, testing algorithm that testing isomorphisms. Or if you think about minimum spanning tree problem, you can think about minimum cost basis. I suspect it's probably easy, but I didn't think well enough to say it's easy. But my feeling is anything mentioned here might be really easy for vanilla and ridiculously hard for this model. So in this model, almost nothing is known. Circuits, connectivity, automorphism, isomorphism, minimum cost basis. Yeah, basically nothing is known. So feel welcome to study and explore this interesting field. I only recently started to learn things about matroid, but it's really interesting. And you don't really need to know matroid to do research about matroid, and I found that's really interesting part. Okay, so thank you very much.
Thanks for the great talk. Okay, in case you have some questions, let me pass you the mic so that we get it recorded. That's why we have the mic. Any questions? Okay, let me start. Okay, so sorry, I have some silly questions. So you were showing definition of colorable through the matroids. I was wondering, is it equality for graphs? Sorry, I mean,
I believe so. It's offset by 1.
It's offset by 1.
Yeah.
So you mean like it's it's always -1, or it's always between this and -1?
No, it's always off minus 1.
-1.
So it's actually very easy to see. I can draw it here. So you in the graphs, chromatic say it's 4. So your graphs looks like this, right? It's a k-partite, and then you just take three parts, and then they must cover everything, right? Because all the edges here, you must have one end that's here.
Yeah, that part I see. How do you see the other part? Like that?
The other part, I don't know. Maybe it's not true.
Okay.
Okay, I don't know. Basically I get all definitions from Peter, and I just whenever I want to study a problem, I go to his office and say, "Give me a definition."
Okay.
Critical numbers like, or chromatic numbers log or critical number or something like this?
Oh, log? Oh, log.
Sorry, it's always it's a range. What is it?
There's some problem with like.
Okay, so forget what I said about
Okay.
of one, set by one. It's
Okay, we can for now take it offline and return to that. Any other questions? Okay, I have another question. Guys, you need to come. There was this not vanilla model, like coffee thing, where you had the question, where is the basis? So, so here I didn't understand. You now don't fix a basis anymore. You fix a sufficiently large collection of vectors and hope to generate other things through that collection?
Yeah, it's a bit sensitive. So basically, I don't want to say, okay, this matroid, the rank is what, okay, and then I fix the basis with that rank, right? But rather, I just wait until I know that with high probability, the next vector I'm going to add is going to fall into the span of the previous ones. And then I just don't care if I'm going to get something out of the span, which means it will increase the rank of the matroid. So I just delete that one because I only care about looking for a minor. So if I add a column that I don't want, I just delete it.
I'm sorry. It looked like you were. Sorry, there was this kind of like you estimating the probability that 3 vectors from the previous ones are giving to you a vector in the second part of the partition. Was the first part in this case a basis?
Sorry, I didn't get it.
You had this matrix P.
Yeah.
And then you were saying, you were estimating the probability that exactly as you were estimating for the basis, kind of like, you were estimating the probability that it will be.
Okay. It's a very good question. The only thing is, it's not a basis.
Okay.
Yeah, but it's something, close enough to a basis. But
So you mean it's independent?
It's
still-
independent.
Okay, it's
Yeah.
independent. Okay,
Yeah.
so my question was it sorry. My
Yeah,
question
yeah.
was
Otherwise,
it's independent?
I won't be able to get the invertible nature. I mean,
Right,
I have
right.
to I have to do row operation to make it all one. So in that sense, yes, it's just not the basis of the matroid. But
Okay.
I'm allowed to delete something, so I just make. In some sense, I just make the rank smaller if I wanted to.
Sure.
Yeah.
Any more questions?
So the coloring you show, the row coloring, it's equivalent to vertex coloring.
Yes.
Can you do edge coloring, like coloring columns and studying
think-
Ramsey property of
Yeah, I think
matroid?
Peter is better to answer this question. I even didn't get it correct, like log thing. You said it's log, right? I don't know, actually. So yeah, even after he gave me the definition, sometimes I have to look at it and think why it is an analog of the graph thing, and sometimes I just get it wrong. So it seems maybe the connectivity, I hope it's correct, but chromatic number is wrong. Wait a minute, if it's a log, because the critical number can only get to n, right? That's still correct. I mean, we proved it. So it's log of what?
So the correspondence between, what is it?
So,
If you look at a binary matroid or something.
okay.
I don't want to say something incorrect now.
We need Peter Nelson, it looks like.
So the,
The number of cuts required to cover, the number of co-circuits required to cover the ground set. Yes.
Sorry.
I mean, that doesn't make it clear that it's more.
So you're looking at the your collections of vertices that form your independent sets
yeah,
in your coloring, and they naturally form a bunch of cuts in the
that's right.
and as a result, the minimum number of cuts required to cover the ground sets will be like all the. It's
Oh, okay.
Exactly how it goes.
And that's critical number.
Yeah. That's the definition of co-circuits.
So does that mean it doesn't mean it's a log of the number of vertices, right?
No.
It's a
It's,
it's a log of
what do you think
partition.
the chromatic number is? Something like this,
Yeah.
the corresponding.
It's more like a log of the number of partitions or something.
Um,
Or ways
yeah,
to
yeah,
partition,
yeah.
right?
Yeah.
Yeah. Okay. And okay, so then that makes a little bit sense, because then I feel it can. I mean, it has to be able to reach to the case that the critical number reaches n, if the rank of the matroid is n.
yeah, I mean, I don't think you can say just log it.
Exactly. So okay, so maybe put it right is maybe that you can find analog if you think about the exponential of critical number. Maybe you can somehow find a connection to the chromatic number in some way, but also not immediately chromatic number. It has something to do with the way of partition vertices according to valid coloring, I guess.
think Peter and Jim,
Sorry.
maybe if they were to redefine critical number, they would define it different. So
Oh.
that it agrees with chromatic number.
Okay, maybe they should use my definition.
Thanks again for talk. Thanks for the comments and the questions. Yeah, I guess like the schedule moves on for visiting students, and yeah, let us take all other questions offline. Thanks again.
Yeah.